Hello, everyone. Welcome to today's Webb's First Images Unfold the Universe with Webb Scientists event. Today is a remarkable moment in the history of astronomy. With the unveiling of the first images from the James Webb Space Telescope, we are getting the first look at the different capabilities of this powerful telescope. And just wow, what a first look for everyone here. My name is Dr. Quyen Hart, and I'm a Senior Education Outreach Scientist and the incoming Web Science Communications Lead at the Space Telescope Science Institute in Baltimore, Maryland. STSCI is the home of the Mission Operations Center and the Science Operations Center for Webb. I'll be the moderator for our expert panel discussion today. I'd like to briefly introduce our four scientists. First we have Dr. Nicole Colon. She's an astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. She is the James Webb Space Telescope Deputy Project Scientist for Exoplanet Science. Exoplanets are planets around other stars. We have Dr. David Law. He's an astronomer at the Space Telescope Science Institute, and his expertise is in galaxies, both near and far. Next, we have Dr. Stefanie Milam. She's the Deputy Project Scientist for Planetary Science for Webb. And we have Dr. Klaus Patapadin. He's an Associate Astronomer and the James Webb Space Telescope Project Scientist at STSCI. He works on the formation of planets and the origin of our own solar system. So, welcome everybody. I know we've all had a really busy day from the unveiling of the first images starting yesterday and then today. And we know that it's been really, truly exciting for the world to see this. So for our audience that are all over the country right now, so welcome to you all to this event. We'd like to share with our audience here a little bit about you all. So we're in a very special place in history right now. So I think the audience would be really interested to hear about how you came to get to where we are today. For example, you can talk about how you became a scientist and what did that path look like? Nicole, why don't you start since you were introduced first?
Absolutely. Thanks so much for the introduction. Yeah, just to tell you a little bit about myself, growing up, I was very much into science fiction, and I loved thinking about where aliens came from and what their home planet was like. So honestly, my love for astronomy started back when I was a teenager, and it just moved forward here. And I've since worked on the Kepler mission, which started off a revolution in our knowledge of exoplanets and understanding how many are out there. And now it evolved to work on James Webb, and that's where I am today.
Great, thank you, Nicole. So next, the same question to David.
Okay, hi. I guess for me, at least, then, my interest in astronomy really came about from starting back in high school and starting to study math and physics and everything like that. And I remember the thing that I found just absolutely fascinating was gravity. The fact that we could just write down really simple equations that could tell us about how things in the universe moved. And that was really just incredible to me, that we could understand how such complicated things, how so many distant things across the entire size of a universe moved and formed into the things that we could observe in our skies. So that's really what convinced me to study astronomy when I was an undergraduate in college, and then go on from there to say, wow, there's so much cool stuff we can study in the universe. And now galaxies in particular really spoke to me, since they're really the building blocks of whatever it is we see in the universe out to the very largest distances. So I've been trying to study them ever since then, all the way from the very nearest galaxies in our own Milky Way out to the very most distant galaxies where we can see the very first things starting to form.
Great, thank you very much, David. Next, Stefanie, could you tell us a little bit about your path towards astronomy and solar system astronomy?
Absolutely. So I grew up in Houston, Texas, and when I was 6 years old, I had a field trip to Johnson Space Center And I came home from that field trip and I told my parents that I was going to work for NASA someday. My background is actually in chemistry, and I was working in an environmental laboratory and decided that I wanted to take my chemist expertise from a room washing beakers and running scientific equipment to the entire universe and using telescopes to study chemistry, not only in our own solar system, but also where other solar systems or planetary systems are actually being formed. So I've been passionate about the James Webb Space Telescope since I've been working on it for over a decade now.
Great, thank you so much. Yeah, I'll share my little story. So I am also an astronomer, and I remember looking as a child outside my window in Philadelphia, and I saw one object through the window because there was a lot of light pollution in a big city. And I just remember thinking about and looking out my window and just wondering what it was. I really thought it was a star. It was actually Jupiter, but still, it was something to look at. And when I started doing my professional work and research, someone asked me, why do you want to study galaxies? And the first thing that came out of my mouth was, they're just really beautiful, and I want to know more. So it could be as simple as that. So for all of you in the audience, young and old, the wonders of the universe can start when you're little. It could start when you're a little bit older. It could start even later. And so wherever that might be, it'll take you in many different places. So our event tonight is to really start you on that excitement of wondering about the universe by taking a look at Webb's first images. So if we could go to the next slide, please. We will start off with the first image that was released yesterday. So here we have Webb's first deep field, SMACS 0723. So I'm going to throw this out to all the speakers, and could someone tell the audience what we're looking at? And I'm going to just see, I'm trying to see, I'm going to see hands from the speakers because I can kind of see you virtually here. So we've got David, why don't you start us off?
I'd be more than happy to talk about that one. So this
How about just take a few words, yeah?
Yep, this one is a fantastic view at galaxies both near-ish and incredibly far, in the sense that we're using sort of nature's telescope to help us look at galaxies way beyond where we could ordinarily see them, even with the power of JWST. And the reason why that works is because the gravity and the cluster of galaxies we're looking at, if you look at the center of the image, then you can kind of see a bunch of whitish blobs. Those are helping to define a cluster of galaxies, and the gravity from those galaxies is so strong it's actually bending the light from galaxies at vast distances beyond them and magnifying them so that we can see things further than we'd ordinarily ever be able to see them in the universe. So those arcs, those red streaks that you see in this image, background behind the cluster that are getting lensed and warped into these weird shapes, and we can see them a lot more easily because they're magnified and study galaxies out to incredible distances. And of course this field is rich with other galaxies as well at a variety of different distances, so there's just an incredible wealth of cosmic time that we can study in an image like this.
Great, thank you, David. I just remembered I did want to remind the host sites. This is for the Q&A that the host sites have access to. When you put questions, as you're hearing our scientist panel, our panel of scientists talk about these first images, and there might be questions that come up for the host sites, you can drop your questions into our Q&A. If you'd like, you can also write down where the question is coming from. It's coming from Baltimore, Maryland, for example. And if you really would like to add this too, you can also say it came from Maya, age 15. And so as we look through, I have a window over here with the questions, and we're going to look through those to ask the scientists these questions. For the other panelists, can someone talk more about kind of these rays that we're seeing, kind of these rings, these arcs, these lines that kind of look like they're doing this in the image? And Klaus, just so you know, I can't see your feed, so if you want to speak up, you'll just need to. But I don't see anybody else's hand, so if someone would like to explain those arcs.
Yeah, I can speak to that. I think you'll see some of us who are sitting here Carter, we're a little bit distracted because there's this crazy thunderstorm going on right now, and our lights are flashing, and I can't see more than 3 feet out the window because there's just so much rain. So, so if we suddenly disappear, it might be a thunderstorm. Just so you're aware. But with that, I can talk about the arcs. So this is one of the things I find really incredibly fascinating about this image, is that what you see is a wrinkle in space-time. Okay? This massive galaxy cluster is bending light from distant galaxies behind it, and when it does that, it creates these arcs and streaks you see around. So these are actually, if the cluster wasn't there, these galaxies would be much smaller. They would be much fainter. So what the cluster does is it both makes distant galaxies appear larger and brighter, and this is something that helps us get an additional boost to our ability to understand these very distant galaxies whose light has traveled for more than 13 billion years by using this cluster. So one of the reasons we picked it for one of the first images.
Thank you, Klaus. All right, so let's move on. We have plenty more time for questions here, and we'll keep some of the more of the Q&A closer to the end here, and we'll go through the images and then come back here. So if we can move to the next slide. So here we have what is called a spectrum of the exoplanet WASP 96b. So I think I'm going to throw this over to Nicole to be able to talk about what amazing things that Webb has seen when it took a look at this planet.
Sure, absolutely. So this is exciting. It is the first exoplanet data to come from Webb. And what you're seeing here is not an image, right? It is a spectrum. But what that means is we've broken up the light that has come from the star WASP 96 as it's filtered through the planet's atmosphere. And we've broken that down to create these data points here that you see. All the little white points are data. And what this is showing us is that in the atmosphere of this exoplanet, there is water vapor that is absorbing some of the starlight and causing these bumps that you're seeing in the data. And you could see that even without the blue line here, which is a model. You could see by eye clearly that there's water in this atmosphere, which is really exciting. And even so, there was a best fit model to indicate that this is just a first look. It's the model, there's going to be more advanced information coming from this, but basically we understand that there's water vapor and that there's evidence for hazes and clouds in the atmosphere as well, because the size, the amplitude of the water features are not quite as large as predicted if it was a truly clear, like cloud-free atmosphere. So this is just the beginning. This is a Jupiter-sized planet. It's very low density, about half the mass of Jupiter. And so we knew that this would be a good target, that it is fluffy. It has a big atmosphere that should contain a lot of water. So it does. So that's great. And now we can move forward from here and start to look at other types of exoplanets ranging down to Earth-size planets and start to collect data just like this and across even more wavelength ranges, because this covers just a tiny part. Not a tiny part, but just one part of the infrared.
Thanks, Nicole. Could you elaborate for the audience, how does the James Webb Space Telescope get this data that we see here? Because you mentioned it's at different kinds of light and certain amounts are bringing out the water. So how does that actually happen in the telescope? Right.
So this planet, WASP 96b is the planet name. This is what we call a transiting exoplanet. So what we see actually is an indirect effect. We look at the star and we measure how the brightness changes over time. And with that, we'll see a big dip in the brightness as the planet passes in front and blocks some light. But then what we can do is take that exact light and break it down, because as the planet passes in front of the star, the planet has an atmosphere around it. So the atmosphere also passes in front of the star. And so with that, we can break down into spectroscopy as you see here. And so there is a light curve of this, as we call it, of the planet passing in front of the star, which we can come back to later as well. But that's how we get there. Or I think we're trying to move there now. So.
Right. Travis, you moved to slide 13. That should be the slide that Nicole is referencing.
Thank you. Oh, perfect. Yeah. So you can see how beautiful this is. Just what we call just a white light curve. So if you just took all the light collected from the nearest instrument in particular, you just measure the brightness over that entire wavelength range in the infrared, you will see before the planet passes in front of the star, it's just flat. It's just measuring the starlight, and then the planet passes in front, the starlight gets blocked, but the planet has an atmosphere, so that actually blocks the extra light, and that's what causes those bumps and wiggles when you break it down. And apologies for the thunder if you're hearing that.
Well, thank you so much for breaking that down for the audience, that the Webb Space Telescope here can break up the light to see the signatures of different molecules in the atmosphere, but it also can detect the planet when it passes in front of a star. And that signature, Webb is seeing this in some amazing detail. So that's really phenomenal. So thank you for that explanation. All right, if we can go back to, I think we are now on slide 4. Great, so our next first image from the Webb Space Telescope here is a planetary nebula, specifically the Southern Ring Nebula. So let's throw this out to our panelists. Why don't you walk the audience through what we're seeing? What is a planetary nebula? There's 2 images here. Why do we see 2 images? What's so unique about that? And what kind of cool features might we be seeing here? So who would like to take this? Stefanie, go right ahead.
This is one of my favorite images that we've released, so I am very excited to talk about it. So we're seeing 2 images from 2 different instruments. So on the left-hand side is the near-infrared image of this dying star. So this is a really old star that's already gone through its whole planetary phase, just as our solar system is going through now. And the star, once it starts to die, starts shedding all of the mass of that star. And when that happens, we see these sort of epic periods of giant ejections of mass, which is all dust and gas. And that's what you actually can see in these images. And so you see these sort of like arc structures surrounding the central star, which you can see in actually both of the images. And this is basically different phases or different epochs of mass loss, which are quite extreme. The level of detail in these pictures compared to some of our predecessor images of this particular object, or the Hubble Space Telescope images, for example, is just absolutely immaculate. You can see tiny little structures billowing through all the ejected material. There's dust that's sort of coiling around. You see bright arcs. You see very dark arcs. And even more surprising and amazing in this image is that you also can see background galaxies that appear quite bright in this image. Galaxies are now a contaminant in almost everything we look at with the James Webb Space Telescope, which is absolutely mind-blowing. But what I love even more about these 2 images is the right-hand image, the mid-infrared image. This is where we can actually see evidence of and observe the second star in the system. We knew that this was a binary star system, but resolving that second star was something that was quite challenging to do, and you can see it in this mid-infrared image. It's that little red dot next to the center blue star. This is absolutely astonishing, the level of detail that we can get with these images with the James Webb Space Telescope. And not to mention that all of these instruments actually have the capability to do the spectroscopy that Nicole was just talking about, looking for those key fingerprints of different kinds of molecules or atoms in all of these environments so that we can really understand the physics, the chemistry, and the dynamics going on. So there's a whole new world of study ahead of us.
Thank you very much, Stefanie. And I just saw Klaus's hand.
Yeah. So, and I just wanted to highlight as well that I think this pair of images, because the two images, highlights that how many infrared colors there are. Right? So you might think that infrared, oh, it's a color, it's infrared. But it's not. It's actually many, many colors we just can't see with our eyes. There are more infrared colors than there are visible colors, and you can see there's so many, in fact, that we need more than one camera to see them all. And that's why we have two images here, because one is taken with a camera that works in near-infrared colors, so that's one section of the near-infrared colors, and the other one is taken with mirror that works in mid-infrared, so there's another part of the mid-infrared colors. And the different colors show us very different things. So I just wanted to highlight that there are so many infrared colors, and that's one of the things that makes Webb so powerful.
Klaus, I'm going to follow up with a question from the audience that's related to what you just said. So you mentioned that there's so many colors. So there's a question in the Q&A. These images are colored by the different infrared filters. Is it possible to convert these to true color images?
That's a great question. These are true color images because infrared colors are just as real as the ones we can see with our eyes. It's just it's not a limitation of the electromagnetic spectrum. It's not a limitation of the world. It's only a limitation of our human eyes. So the colors you see here are very real, just as real as a Hubble image. It's just that you would need infrared sensitive eyes to see them.
Thank you, Klaus. I'm going to open this up to the rest of the panelists. Would you like to add anything to, what was your first reaction when you saw these images for the first time?
I guess I can just add that what really stands out to me, I think, is looking at the right-hand image. It really encapsulates the new information that we get when we're able to look out at the mid-infrared wavelengths we've got access to with Webb now in such depth and detail for the first time, in the sense that now you can see what the very center of this nebula looks like in the two, and on the left there's just a single star, and on the right there's two stars, and you see this one very red star just now popping out suddenly, super obviously. You can see it because you can see down to all the layers of dust to see this super buried source, and it's just really exciting to me that we can see things before now that were pretty much just unseen before. We have the new ability to find things.
This is another case. Yeah, I mean, I don't know what I can add beyond what has been said. I think I really like Stefanie's point about, things. Any image now we're taking gets photobombed by galaxies in the background too, because it's showing you, the universe is just so dense and rich, right, with information waiting for us to discover and find it. And that's why we have, needed these infrared eyes. And as Klaus was saying, all these infrared colors to see what is going on here. And the same is true for all the other images, right? There's just so much to learn, and this is only the beginning.
Yeah. I was definitely I was just marveling at the detail in these images and trying to see what's different, what's the same in the left and the right, and the binary star in the mirror image on the right hand side. That was just amazing that they had never seen that before, and here it is right there. So there's a question here from the chat related to this planetary nebula. So are both stars in the Southern Ring Nebula system dying? So I don't know that question, so I'm going to throw it back to our panelists. Are the two stars in this ring nebula on the right-hand side dying?
Yes, I can take that. It's a great question. So the star that has given rise to this nebula is a faint one. It's the one you can't really see in the near-cam image. It's the red one in the mirror image. It's a stellar remnant now. It's a white dwarf that is incredibly hot. Like once a star has cast off its outer layers, it's essentially exposed this intensely hot stellar core, 100,000 degrees hot, and that is what also lights up the whole nebula. The other star, the one that appears bright in both near-cam and mirror, the blue one, is not dead yet, or as far as we know, approaching death. Of course, all stars eventually die. So it's the red one, and you see in mirror that's dying or dead already, let's say.
Thank you very much, Klaus. I did see another question about this planetary nebula. So we have a question: how does planetary nebula imagery help us to understand our own solar system? That's a great question. So who would like to take that question?
Sure. So planetary nebula is a total misnomer. It is really not a planetary system. As I said, this is well after a star has evolved beyond having planets around that star. So it's gone to a giant phase, and then once that giant phase becomes unstable is when it starts losing all of this mass. But even in the phase just before this, that red giant phase, the star gets so massive, it actually will usually consume most of the planets in its own planetary system. So when our star evolves to this phase, it's going to, get a radius that's about the distance to Mars. So it's going to swallow all of our terrestrial planets well beyond it enters this phase. But one thing that's really interesting about planetary nebula, and something that we actually had discoveries with other telescopes, including the Spitzer Space Telescope, is that sometimes when we get to this phase where we're losing all this mass and that center star becomes exposed and it's extremely hot, as Klaus was saying, sometimes we see what we believe are what's been called cometary knots. So there's these what look like comets or some objects with dusty tails that are being blown off from the center star. So if you would look into the arcs of some of these images, you might see something that looks sort of like that. And we believe that this is sort of the remnant dusty, icy material, maybe even planetary bodies, that's now being dissociated, that was in the outer planetary system of these former stellar systems. So while it is called a planetary nebula, it's not necessarily associated with a planetary system, the way that Nicole has explained to us with exoplanets, or as you might think of within our own solar system.
Thanks. I always want to say, Stefanie, thanks for bringing up that story, because it's just about the remnants of the dead planetary systems you see in white dwarfs, because it's one of my favorite stories, that you look at these white dwarfs and you see sort of the skeletons of the dead planetary system that was once there. We can see it was there, and it's now all gone and destroyed, but we can learn something about it.
Thank you very much for sharing that with us. Okay, so I think we'll move to the next image that was shared today. So next slide, please. So now we're going to talk about one of my favorites, galaxies, this interacting galaxies, Stefan's quintet. And I'm going to throw this over to David, who is an expert in this area, and he could start us off with, what are we seeing here?
Sure. So what you're looking at here is actually multiple galaxies similar to our own Milky Way, except instead of living largely in isolation with only one or two very small nearby neighbors, what we're seeing here is galaxies that have lots of very big neighbors, and they're all interacting with one another very dynamically. So the gravity from these galaxies, they're all very near each other, except for one, which I'll come back to in a minute. They're very near each other, and the gravity from these galaxies is actually ripping stars and gas out of the other galaxies nearby as they merge together. So this is one of the major means by which galaxies grow, from the first tiny little nubs in the early universe up to the giant spiral and elliptical galaxies that we're familiar with today. They grow by smashing together lots of other little galaxies. And that's really what's going on here. We're taking now a number of galaxies that are in this compact group that are in the middle of merging together by gravity. And if we could watch the system for the next hundreds of millions or billions of years or so, we'd see them continue to merge together and form one giant galaxy from all of the individual components. So what you're looking at here, if you look at kind of that central region, the bit that has the two brightest yellow dots near close to one another, that's actually two galaxies that have just recently flown by one another at 1,000 kilometers per second. And as they go by, they're starting to shred off stars from one another and pull off gas and things as well. you can see giant shells of stars coming off it in that galaxy at the top as well. But these are things that have been pulled out of the galaxy by yet another galaxy that's interacting with this group, kind of off screen, off to the top left or so. What's particularly fascinating about this image, though, and what's really new and what Webb brings to bear on this is if you look at all of the red and gold areas of this image, that's showing you where the gas is. We're seeing that with the MIRI camera on Webb. And so while the stars are kind of showing up in sort of the yellowish white, the gold and red is the gas. That gas is what ultimately goes on to form stars and is also contains the dust that stars produce when they die. So it is the thing that stars form and the thing to which they return when they are done living. And even while these galaxies are merging together and tearing stars off of one another, they're triggering collisions in all this gas that they're ripping out from each other in the red and gold and forming new stars as they go. So this is going to be quite a cluster to continue to watch for many millions of years to come as it forms new things and continues to give new spectacular views.
Thank you, David. So what might be a prediction of what this could look like after they interact together? Are there models? Do we, what might happen a million, hundreds of millions of years down the road for this particular group of galaxies?
So this is something that's known as a major merger in the sense that we're throwing together into the blender a lot of really massive things that are all interacting with one another. And what that does to the stars is it tends to scramble up all of those orbits pretty effectively. So if you started with some kind of a disk, a spiral galaxy like our own Milky Way, interactions like this are going to destroy those disks. Now, that disk is just going to get scrambled around. And probably what you're going to see if you look at something like this in another billion years or so, you'll see more of a elliptical type galaxy instead, something that's scrambled up all those orbits and it looks more round and smooth as over the course of many hundreds of millions of years, those stars sort of rearrange themselves onto new orbits. And you'll probably pick up bits of new star formation going on in various outer regions of that galaxy. But largely it'll be converting it to something more like the elliptical galaxies that we see today.
Great. Thanks for painting us a picture that, it's a little ways down the way, but
you got to wait around a little while to see exactly what happens. And now some of these galaxies actually aren't going to be hanging around for that party. So I should add that galaxy on the left-hand side there, that isn't actually even part of the collision at all. It looks like it is. It's right there with all of the other galaxies, but it's actually about 5 times closer to us than the rest of the galaxies in the set. So that one's just going to go on its merry way while all the rest of them do this merger in the background.
Great. So while we're on this picture, another question came in here that I'll open it up to all the panelists. Why do all the Webb photos of all the bright stars have the spikes pointing in a north, south, east, west direction? Is that actually visible or just part of the process photo? So who would like to address that question? So these are the spikes in the particular image. I think the person is referring to, there's 2 bright star-like objects in the upper right-hand corner. There's a few fainter ones near, this bar near the bottom there. So who would like to answer that? Go ahead, Klaus.
All right, so this is an effect you see in any telescope. You see it in any camera. What happens is that you see that light that is coming in is not particles, it is waves. And so light that comes into a camera, that wave interacts with the shape of the aperture of the camera. So normally if you have to have a photo camera, so you have a round aperture, and so that creates a simpler shape. Webb doesn't have a round mirror, it's a hexagonal mirror, it has 6 sides. And so what happens is when the light wave comes in and it interacts with that funky shape, that's 6 sides, that's what creates those spikes that you see coming out. So you can think of it as sort of it's a fingerprint that you can use to identify the telescope that took the image. So if you go look at a Hubble image, that has 4 of these spikes. We call them diffraction spikes. you get some as well from the fact that there are some other obstructions in the aperture and so on, but that gets too detailed. So Hubble has 4, and a little bit extra. Webb has 6, and 8, depending on how you count. So you can always see this is a Webb image by that shape of the star.
Yeah, that's we're gonna have we just are starting this new era of astronomy and having these amazing Webb photos, and we have Hubble photos too. So this will be one of those telltale signs to be able to distinguish between a Hubble image and a Webb image based on these spikes that you see in the images. Thank you, Klaus, for the explanation. All right, so we're going to move on to our next slide here. And so here we have the star-forming region in the Karina Nebula, and it is also, you might have heard it referred to as the cosmic cliffs. So who would like to share with the audience what we're seeing here? This amazing, this is one of my favorites. Yeah, I really do like clusters, but this is really, really, really close. Yes, Nicole, go right ahead.
Yeah, I can start off. Yeah, as much as I love the exoplanet spectrum, this one is just so stunning. There's just so much detail here. I mean, honestly, all the images, right? If you zoom in, there's so much detail hidden, and that's the exciting part. Is what you're seeing here is these dense regions of cloud of gas and dust clouds that are coming together to form new stars. So with the infrared images, so this is with the NIRCam instrument, near infrared light, you are able to see through the dust clouds into the cores to see the stars that are bright and shining and forming new stars, and also presumably new planetary systems. So there's this, as the stars form, all this clouds of gas and dust collapses, and it starts swirling, and there's additional material left over that forms a disk once the star is fully formed, and then from that disk is how planets form. So it's all tied together in this process. And so this is an early stage of the process when stars are forming. But without the infrared light, you would just see the dust clouds in the visible light. So you have to have the infrared to see through the clouds. And also, just like the other image, you see a lot of those stars with the diffraction spikes. So those are really bright foreground stars in front of the cloud, essentially. But there's just so much detail here. So I definitely encourage people to, zoom in and understand this cliff and look at it and find detail to see, okay, all the pockets where stars are forming, because it's incredible. And then, yeah, if anyone else wants to add anything, because.
Oh, yes, please do. So Klaus, David, Stefanie, please share what you're thinking about when you see this beautiful view in front of you. David, I just saw your hand.
Yeah, I can just echo what you were saying as well, in the sense that galaxies are the main things that I study, but now this image makes me wonder if I need to reconsider, just because it is so absolutely stunning, both from an artistic sense and also from a astrophysical sense, in the sense of what it can tell us about the formation of young stars in regions like this. And I think one of the things I like about it particularly is that there's regions in it that are already new to us, and we have some ideas about what might be going on there, but we're already learning new things about star-forming regions just by looking at this very first released image of the nebula. And I think it's going to be giving us tons of wonderful information for many years to come.
I have to zoom in to see it.
So Travis, if you can go to slide 21.
So what you see on the right there, you see these kind of yellow, if you look below, there's a star, and then you below it, there are these kind of yellow things that look like a ship, like a ship shape. So what happens is that there's a young star there that is that just forms. The star just collapsed out of the cloud, and when that happens, there's a little bit of rotation, and that rotation spins up material into a disk that orbits the star, and that is where planets are forming. But as the material is moving through the disk, and some of it is crashing into the star, some of that material also gets pushed out above and below the disk in these massive jets. And that's what you see here. So that's a protostellar jet. So that's clear sign that there's a star here that is actively forming at the moment. And what you see is below the star, the jet hits the cloud itself, and that creates what's called a bow shock. It basically plows through the cloud, and it creates a ship-like shape. But what I find really cool here is, and so these have been known before. So what I find really cool about this is if you look in the other direction, there's also a jet, and that jet has punched through the surface of the cloud. And you see like a puff of smoke as a bullet has, of material has punched through the cloud. And you can trace from that star all the way up to the top of the image. There's an arrow there where it says shocks. That's a bullet. And we caught that, and we didn't know it was there, that bullet there. We're just lucky that was still in the field just on the top there. So I find it really cool. And what you can also see, of course, is that the jet in the bottom, the one that's plowing into the cloud, that doesn't get very far because it has to move through this cloud. But when it goes out of the cloud, it's just going through empty space. And so you went much farther away. And that's why it's way up there. So there's action here. There's like things happening all the time. The thing is churning and brewing and making stars. Still in an astronomical time scale, but you can actually, if we come back and take an image of this again in a year or two, we can probably see things moving. What is helpful here is that now you see a number of stars that are red and a number of stars that are blue, very clearly, right? Red, blue stars. This means the red stars have hot dust around them, and we know today that hot dust is those planet-forming disks that they have, like pretty much all young stars. These are stars that will end up being like the sun one day. So you see solar systems forming here, and what an infrared telescope like Webb does is it makes it super easy to find them. Like whenever you take an image with MIRI of a cluster like this, you just pick out the red ones. Those are the ones that are forming planets. The blue ones, they're regular stars. They're probably in the foreground and the background, and probably not young. So it just makes it really easy to figure out what's what.
Thanks, Klaus. We just saw some really amazing images, talked about some amazing description of what's going on, and I could see the questions in the Q&A. So we're going to pivot towards the general Q&A, and I'm going to start it off by asking you, Stefanie, because you work on things in the solar system. And one of the questions that's been upvoted a lot is, will JWST be used to search for and study objects in the Oort Cloud? So if you could describe what the Oort Cloud is, and then that question.
Absolutely. So for those that don't know, we have multiple regions in our solar system that contain planetary remnants, or the crumbs left over from when our planets formed in our solar system. And these major regions are known as the asteroid belt, which is sort of between Mars and Jupiter. And sometimes we get asteroids that come in even closer, near-Earth asteroids that come really close to Earth. We also have a region called the Kuiper belt region. So this is sort of out by Neptune and Pluto. There is some smattering of small objects that breach the asteroid belt into the Kuiper belt and vice versa. But this is where a lot of comets actually live. So comets that come around the sun pretty often or regularly. So by regularly, that can mean anything from every few years to every 70-something years, like Halley's Comet. But then we also have a region, a theoretical region known as the Oort Cloud. So this extends even beyond what we know as the Kuiper belt. And it's sort of this sphere that encompasses the entire solar system. So you can think of a giant shell that's full of cometary-like objects. And we believe that this actually exists because every once in a while we get a new comet that comes into the solar system that has been upset from its current location and pushed in towards the sun. But the orbit of these objects are something on the order of like tens of thousands of years. So we know that they're coming from somewhere quite far, but not necessarily coming from another planetary system. though we do have those now as well. We do know that interstellar objects come into our solar system. But we believe that these distant or long period comets are actually coming from something called the Oort Cloud. Now, to study the Oort Cloud is something that's very challenging to do because it's very far away. So using ground-based telescopes is very challenging. And even something as sensitive as the Hubble telescope or the James Webb telescope will have quite a bit of challenge trying to study what these objects actually look like, what the density of the Oort Cloud actually is, or any of those types of things. The James Webb Space Telescope specifically is not really a surveying, searching kind of a telescope. We're not going to be taking big images across the sky, hunting for new asteroids or hunting for exoplanets the way the TESS mission is currently doing, or the Kepler mission did prior, or even what some of these near-Earth asteroid surveys are doing. The James Webb Space Telescope has a very narrow angle that it can actually see in any given moment of the sky. And so what that means is we do really, really well at honing in on one object and studying it very, very well, or that grain of sand held at arm's length. We're not looking at, entire portfolios of the entire sky. So that being said, to study something like the Oort Cloud and understand it, what we can do with the James Webb Space Telescope is study the objects that are coming from it. So these new comets or new dynamic objects that are somehow perturbed and coming into the inner solar system. And that is something that I'm extremely passionate about and what I actually do for a living as I study these comets that are coming in. And it tells us a lot about what that remnant material is. So as we just saw this beautiful Karina Nebula image, a lot of that gas and dust that you see there is not going to make it into the star itself or a planet. Some of it is actually going to be something like our asteroid belt or these cometary regions around those planetary systems. And so having that comparison that we can study the whole process of when these stars and planets are actually forming, studying planets around other stars and maybe what their asteroid belts look like, and even studying our own solar system, the preserved or leftover crumbs from when our planets formed, all the way into our own planetary bodies in the solar system. Help us pull that picture together and understand what that process actually looks like. And our solar system, whether or not it's unique or whether or not it's just like all the other ones that we can observe.
Great. Thank you so much, Stefanie. All right, we got another question here. So we have a question about the exoplanet. Planet WASP 96b was found to contain water in its atmosphere. How common is it to find atmospheric water on other planets? And would this be a planet where astrobiological life could be developing? So I think this is for you, Nicole.
Right. So water, first off, is made of hydrogen and oxygen, and those are two of the most common elements in our universe. So actually, just by the process of how planets form in the first place, we've been talking a lot about that because of the star forming region, right? And how you evolve from a disk of material around a star that's formed into a planet. Well, that disk contains all these basic elements like carbon, hydrogen, oxygen. So as a planet is forming, it's actually quite common or expected to be common that it has water accreted into its atmosphere during the formation process. And that's planets of all sizes. So this is a gas giant, Jupiter-sized planet, and it's not one that we're expecting to see any signs of astrobiological, indicators of any kind, because it's not just giant, it also orbits very close to its star. So it orbits within about 3.5 days. So our year on Earth is 1 year, right? It's 365 days. That's how long it takes Earth to go around the sun. And WASP 96b takes 3.5 days to go around its sun. So it's very close to its star. It's very warm. It's giant. So it's not expected to be a place that is hospitable for any kind of life, essentially.
Understanding the atmospheres of these exoplanets is going to be really amazing to get these signatures that we haven't been able to get before. So that's really exciting to know what's in those atmospheres. And Webb is going to be able to do it like no other telescope has. So it's exciting. So some more questions here. We have a question, with the understanding that our universe is expanding, is it part of JWST's mission to provide significant contributions to our knowledge regarding the age, size, and shape of the universe and the location of our solar system within it? This is from Harvey Hamill, the Battle Point Astronomical Association in Bainbridge Island, Washington. So I'll put that up for, it's all David, go ahead.
So I can speak a little bit to that in the sense that there's a number of things that Webb's going to do for us that are going to help us learn more about cosmology and the early formation of the universe. The most direct one is what we want to see is where the very first galaxies came from. We want to try and understand when the very first stars and the first galaxies turned on and started radiating and ionized the universe. We'd like to see when that happened. How long ago was it? What were these galaxies like? And how did they turn into the galaxies that we're familiar with today? But perhaps more directly to the question of cosmology, there's actually a tension at the moment that we're hoping that Webb might be able to help with as well. In the sense that if you try and understand how the universe is expanding, how small it used to be in the past, how big it is today, how rapidly it's growing bigger, there's actually a few different ways that you can go about trying to measure what the expansion speed is, the so-called Hubble constant. And we're getting really good at measuring that in a number of different ways now. And what's getting really fascinating is that our measurements are starting to disagree with each other. And it's getting to the point where you can't just wave it off and say, no, there's uncertainty. They're actually starting to point to maybe there's entirely new physics in there. And what we're hoping that Webb can do is, by virtue of studying certain kinds of stars and helping us refine the ladder to how far away different stars and galaxies are, both with its depth and its infrared capability, it can help us figure out exactly how big of a discrepancy that is and how much new physics might really be waiting for us in our understanding of how the universe came to be the place it is. So I think that's something to watch this space here to see if it can tell us more about where we all came from in that sense.
Sounds really exciting. Yeah, when we talk about the universe is a immeasurable place with lots of things in it and lots of things that Webb will study. So we have a few more minutes, so I want to get to some of the top questions, and maybe we can do some quick answers so we can get some responses, answers to some of the questions. So I think this is for you, Stefanie. What are the closest objects that JWST will be getting data on? Can you give any clues?
That's a great question. JWST can actually observe near-Earth objects. So as long as they are within the JWST, what we call field of regard, or that tiny little viewing perspective that we have with the telescope, and we don't point it towards the Earth and we don't point it towards the sun, we can actually observe these small objects as they come close to Earth. And that's something we absolutely plan to do all the way starting actually very, very soon. We even did some commissioning tests on studying some asteroids. Because they move so fast in the solar system compared to the other planets in our solar system, we actually tested how well we could track objects moving across the sky with the James Webb Space Telescope. And asteroids were our primary candidates for doing that. And so we've demonstrated that we can now track these objects that are moving fast, that are coming pretty close to Earth. And it's something that we have a high priority in doing as far as solar system science goes for the next 20 years.
Great, thank you. So how do we pick locations in the sky to look at with JWST, that's in reference to the images today, and how long did it take to process them and make them public? So I think this is a question for Klaus, who has been deeply involved with this process. So how about a quick 2-3 minute explanation of what's going on? What give us a glimpse into your world over the last 6 months.
Sure. Yeah, that's great questions. So the process of picking the first images is something that's been underway for years, because we knew we had to do this. Already, back in 2016 is the first time we started thinking about it, just because we know we were going to do this. What are we going to do? You know, it has to be something spectacular. It has to be something that really shows off the science that Webb can do, and not just one kind of science, but the breadth of science. It has to show off all the instruments. And so there was a few people who got together and thought about that. And they ended up with a very long list of targets that gave us some flexibility at the end to actually observe what we could observe, what was visible at the time when we had to observe these. How much time does it take to process one image? I would say probably on average about 2 weeks end to end from actually taking the data on the telescope, getting it down, processing the data to a very high level of quality, handing those off to graphics artists who put them together from monochromatic images that are taken through a filter to these color images that you see, and everything that goes along with it. So about 2 weeks.
Yes, and that's an amazing amount of time. Was a flurry of activity in the month of June that many of us would be really, really will remember for our lifetimes. So we're near the end. So I wanted to throw one last question for our panelists and ask you, what is the biggest surprise or the most unexpected thing about one of the first images that you're most familiar with? And then Klaus.
The most unexpected thing, I was blown away with the Miri images of the Stefan's quintet. I can't believe the detail that you can see at the long wavelengths with the resolution of the James Webb Space Telescope. I don't study galaxies, and as has already been said, maybe I need to change my field and start moving towards some galactic science. It was absolutely fantastic, and it blew me away. That's by far my favorite image.
Yeah, I have to say probably. Oh gosh, yeah, probably the Karina Nebula. The detail there. I mean, there's detail in all the images, like I said before, but it's just almost like the fine structure you see, you know, for this object that it's literally looks like artwork. I mean, it's just almost impossible to put into words how beautiful it is, right? And so it's not. I guess I'm not surprised that Webb is capable of this, you know, but it's still a pleasant surprise to see just how beautifully it works kind of like right out of the box.
Okay, I guess for me it was probably just the wealth of galaxies you get in the background of other images. And we knew that Webb was going to see a lot of galaxies in the distant universe. And that's one of the main things that it was built for, was to see these galaxies. But just the ease with which they pop out in any other things you're looking at, whether you're looking at a nearby nebula, a nearby galaxy, or actually explicitly trying to do a deep field, the fact that they just pop out. There's a redshift 4 galaxy. There's a redshift 8 galaxy. They're just dropping out in such incredible numbers that I can't help but look forward to the amazing things that we can do with them in the years to come.
Yeah, I would say for me, I mean, in terms of just plain beauty, the Karina is my favorite. It's my baby. I've looked at that for so long, and it was. I was happy to see that some of the design choices we made, they came to fruition. But I think from a science perspective, it's really the deep field surprised me the most. Not in the sense that we could do a deep field, right? Because we knew how sensitive this observatory was. It was when you look and you zoom in, and I really recommend anyone to do that, to zoom in on those distant galaxies, 10 billion years old. And you may see some smudge with Hubble, but here you resolve these galaxies into structures. You see individual star clusters forming in them like little dots. There's one object we call the ladybug, and it's 10 billion years old. It was a surprise to me. I did not expect us to be able to see that kind of fine structure in the galaxies. Detecting something there, yes, but seeing them as individual, living, almost little creatures was a surprise to me.
Well, thank you so much for sharing all of your perspectives on Webb's first images today. I'm sure the audience really enjoyed hearing your perspectives, what you found amazing, and what we all saw today for the first time. So I encourage you, just like Klaus mentioned, to go take a look at these images online, download the highest resolution images, and really take a look and marvel in that wonder of the universe that's out there. And Webb is going to uncover so many mysteries that we have and answer these questions. So again, I'd like to have a virtual applause for all of our speakers today. Thank you very much for sharing the science of Webb with our audience. Thank you in the audience for joining us today and hearing more about Webb's first images and what Webb will do to unfold the universe. So good day, good afternoon, or good night to wherever you are. Thank you for joining.